In this video, we're going to talk about the Hartley oscillator. Now, this particular circuit only uses one NPN transistor. It also uses an emitter resistor, which we'll call RE, and across the emitter resistor is the bypass capacitor. This capacitor will increase the voltage gain of the circuit. Now we're going to have two other resistors, R2 and R1. These two resistors, they form a voltage divider network at the base of the NPN transistor. Now you could use a collector resistor, RC, or you could use a radio frequency choke, which we'll call RFC. The purpose of the radio frequency choke is to allow DC current to flow through into the collector of the NPN transistor, but provide high reactance to high frequency signals, thus increasing the overall voltage gain. The inductive reactance is equal to 2 pi FL. So as the frequency of the oscillations increase, the inductive reactance increases. And as you increase the impedance of this inductor to AC signals, the overall voltage gain will go up as well. However, the internal resistance of the RFC choke is relatively small compared to its reactance at high frequencies. Next, we have two capacitors known as coupling capacitors, which functions to block DC while allowing AC signals to pass through. So we'll call this C1 and C2. As the frequency increases, the capacitive reactance of C1 and C2 will decrease. Thus, high frequency AC signals can easily pass through C1 and C2. The issue is with low frequency signals. As the frequency decreases, the capacitive reactance increases. So if you're trying to design a low frequency Hartley oscillator circuit, you want to increase the value of C1 and C2, because as C1 goes up, the capacitive reactance goes down. And so that's how you can compensate for the increase in capacitive reactance when dealing with low frequency signals. So you may want to use 1000 microfarads or more for C1 and C2 if you're dealing with frequencies below 300 Hertz, for example. The formula for capacitive reactance is 1 over 2 pi FC. So as F goes up, the capacitive reactance goes down. And as you increase the capacitive reactance also goes down. So that's one formula you want to keep in mind when choosing values for C1 and C2. But if you make them as high as possible, you really don't have to worry about the math that goes with this. Now, the next important thing we need to talk about is the LC network, which controls the frequency of oscillations. So the LC network will contain one capacitor and two inductors, which could be one single inductor with a center tap. Now at the center, you want to connect this to the ground, which is basically the same connection here. And then the other part of C1, you want to connect that to the bottom part of the LC network. So let's call this let's call it C3, and then this is going to be L1 and L2. The total inductance is going to be the sum of the inductance of L1 and L2 plus any mutual inductance that will occur when those two are next to each other. Now the resonant frequency of this LC network is going to be the same formula as always, 1 over 2 pi times the square root of LC. But it's going to be LT times C3. So that's the formula you need to calculate the resonant frequency of this particular circuit. Now let's talk about the output of this circuit. The output can be taken from the other side of C2 and the ground. Now let's say that L1 is 2 millihenries, and let's say that L2 is also 2 millihenries. And we want a frequency of 100 kilohertz. What value of C3 should we choose? So let's ignore mutual inductance just to keep the math simple. So if we want to generate or design a Hartley oscillator circuit with a frequency of 100 kilohertz, what value of C3 should we choose? Oh, by the way, this is the collector supply voltage. Let's not forget about that. So first, we need to rearrange the formula. Ignoring mutual inductance, LT is going to be the sum of L1 and L2. So it's going to be 4 millihenries. And we know that the resonant frequency is 1 over 2 pi times the square root of LT times C3. So the first thing you want to do is you want to square both sides of this equation. So you get F squared is equal to 1 over 2 pi squared becomes 4 pi squared, and the square root symbol will disappear. So we get LT times C3. So what I'm going to do now is I'm going to multiply both sides by 4 pi squared times LT. So you get F squared times 4 pi squared LT is equal to 1 over C3. Then raising both sides to the minus 1, you get that C3 is equal to 1 over 4 pi squared F squared times LT. So once you set your inductance value and you know the frequency that you want the circuit to operate, you could use that formula to calculate the desired value of C3. Now let's plug in the numbers. So we have 1 over 4 pi squared. The frequency is 100 kilohertz. So that's 100 times 10 to the 3, or 100,000 hertz. Don't forget to square it. And then we have 4 millihenries. That's 4 times 10 to the minus 3. So go ahead and plug this into your calculator. Don't forget to enclose all of this in parentheses. So the value that I got is 6.33 times 10 to the minus 10 farads. I'm going to divide that by 1 times 10 to the minus 9 to convert it to nanofarads. So this is equivalent to 0.633 nanofarads. If you want to convert that to picofarads, multiply that by 1,000. So that's the same as 633 picofarads. So that's the value of C3 that you need in order to obtain an oscillation at 100 kilohertz, theoretically speaking. But now, it might be difficult to find a capacitor with this exact value. So what you need to do is you need to combine multiple capacitors to get that value. So let's talk about how we can do this. Whenever you add capacitors in parallel to one another, the equivalent capacitance is the sum of the individual capacitance. So let's call this C1, C2, and C3. So CT is going to be C1 plus C2 plus C3. So we want to get an equivalent capacitance of 633 picofarads. So you need to look at the capacitors that you have and combine them in such a way that you get 633. So let's assume we have two 300 picofarad capacitors. So that's a total of 600. And we have a 33 picofarad capacitor. So in this case, this will give us the desired capacitance that we want, 633. Sometimes you need to do that in order to get the desired capacitance that you want so that the circuit will oscillate at the desired frequency. So that's basically it for this video. Now you know how to calculate the capacitance needed to create a Hartley oscillator circuit with the desired frequency. Thanks for watching.